Welcome to the third talk. Our speaker is Professor Pablo Shmerkin from Department of Mathematics, University of British Columbia. He's going to talk on dynamical self-similarities and slicing. Let's welcome.
Okay, thank you. It's really great to be here. My first time in mainland China. I've been to Hong Kong several times, but have never been to the mainland. So hopefully the first of many visits. I have several Chinese collaborators. I hope to have even more in the future. Okay, so I'm going to talk about the paper that got the prize. So the prize is joined with the Mung-Bu's papers. So I'm not going to assume that you want to remember all of Mung's talk, but at the same time, I'm going to minimize the overlap. So we'll see how well that works. Okay, so here is a special case of the Furstenberg's slicing or intersection problem, but in fact, it is as difficult as the general case. So we have two very simple counter sets. The first very simple counter set is the counter set. So the first one you learned, just the middle thirds counter set. I hope you're all familiar with them. But if you forgot, so this is, as you see, is a product. On the x-axis, you have the ternary middle thirds counter set. And on the y-axis, you have a very similar counter set, but constructed using base 4 instead of base 3. In terms of expansions, it means that we only use digits 0 and 3 to base 4, and forbid digits 1 and 2. Okay, so in terms of dynamics, this set is invariant under multiplication by 3 on the circle, and this one is invariant under multiplication by 4 on the circle. 3 and 4 have nothing to do with each other. And the question is, we take this set now on the plane, this product set, and slice it with the line. For example, the line could be just the diagonal. So what happens if we slice a product set with the diagonal? Well, up to an affine change of coordinates, which doesn't change dimension, we are just intersecting the two sets, A and B. So intersecting the product set with the diagonal is intersecting A and B. And if we change the line, then we are intersecting A with the linear image of B. So this is equivalent to the way that Mung stated in his talk. But as also Mung mentioned, it's much better to think of the problem in this way. We have something in the plane and we want to slice it with lines. And the question is, what can we say about the size? Well, there is one thing I think we can all agree on, and it is that the intersection can be empty. You can imagine that there are many lines that don't hit the product set at all. So the question is not how small this intersection can be, because it can be empty. The question is how large can this intersection be? And large should be measured using some sort of fractal dimensions, such as Hausdorff dimension, because these are all fractal sets. Okay, so this is one problem, and I want to introduce another problem. And the point of the talk is that these two problems, at first sight, have something in common, but not too much. And the point is trying to come up with a viewpoint that sort of unifies these two problems. Okay, the second problem is the following. We defined a probability measure on the real line as a distribution of the following random variable. So it's like a random walk, but where the walker is getting tired at an exponential speed. So the walker at the end of time is going to end up in some random point, and that random point has a distribution, which is mu lambda, the Bernoulli convolution with parameter lambda. So lambda is a real number between 0 and 1. And okay, yeah, you just look at this random sum where you either add or subtract lambda to the n at each step, and all the choices of signs are independent and equally weighted, 1/2, 1/2. Okay, so this is known as the family of Bernoulli convolutions because it is an infinite convolution of Bernoulli random variables. I'm going to come back to this. And there are two very different regimes in this studying this family. If lambda is at most 1/2 and not 1/2, so strictly less than 1/2, then actually the distribution lives on a counter set of the type that we saw in the previous slide. So in particular, the topological support of mu lambda is a counter set that has 0 measure, and so mu lambda is definitely singular. For example, if lambda is 1/3, the measure you get is r to an affine change of coordinates, just the natural measure on the ternary counter set. On the other hand, if lambda is bigger than 1/2, if lambda is exactly 1/2, then this is actually a Lebesgue measure on some interval. If lambda is strictly larger than 1/2, then it is still true that the topological support of mu lambda is an interval. But the topological support is very simple as a set. It's an interval. But on the other hand, understanding the measure is extremely complicated. And if you've never seen this problem before, you cannot imagine how complicated it is. It is an extremely subtle and intricate problem, and there have been many decades of progress, included by people in the audience, but there are still many things that we don't understand. And today, okay, this is a huge area. I'm going to mention only some results and some things that we can now say. Okay, so these are the two problems that I would like to bring into sort of a common framework. And to do that, I'm going to talk about Frostman exponents. So the word Frostman comes from Frostman's lemma, but you don't need to know Frostman's lemma, it's just a definition. So the Frostman exponent, so you have a measure. A measure for me is a finite probability measure on RD. So this is a measure. So you have a measure, and you look at the best exponent. The best means the largest exponent that controls the measure of every ball. Every ball. Not almost every ball, but every ball. So this is a crucial distinction. Let's say no. It's not too important. Let's say no. Yeah, so yeah, good point. Not only I want S to control the measure of every ball, but I want to control the measure of every ball with a uniform constant, which also doesn't depend on the point. So a very, very uniform control on the mass of balls. Because the measure is finite, 0 works. So this is well defined. There is a supremum. So the supremum is not realized, right? But well, it could be. It's not always realized. But we're talking the supremum of an non-empty set. Even this late in the day, we can agree that this exists. It's also it's finite. Very slightly less trivial fact is finite. So let's look at some examples. Suppose that we have a Lebesgue measure on RD, then the measure of a ball is R to the D. So and you cannot do better, it's exactly R to the D, so the Frostman exponent is D. If you have, again, the Miller-Thurst counter set and you put the most natural measure you can put on it, such as the Hausdorff measure, then, because the measure is very uniform, it sees the dimension of the set, and basically it doesn't matter which center you take, all the balls look more or less the same. So this is has Frostman exponent, the dimension of the counter set, which is log 2 over log 3. On the other hand, because we want to have uniform control with every center, you can have a very nice absolutely continuous measure which doesn't have, so you would expect that an absolutely continuous measure should have dimension 1. But if you measure dimension with this Frostman exponent, this is not true. For example, suppose that you have a measure with the density square root of x, something like this, on 0, 1. I wrote 0 infinity, but it could be even be 0, 1. Well, there is too much mass at 0, only at 0. But this already brings the Frostman exponent down. So just having one bad point can decrease the Frostman exponent. So having a large Frostman exponent expresses a very uniform property of the measure. Any questions? I only care about compactly supported measures, but I think you can define it in any case. Yeah, it's not compactly supported, but the radius, I only take radii up to 1. It doesn't matter if it's compactly supported or not. But as I said, instead of 0 infinity, you can take 0, 1. The point is that at 0, it has a singularity. It's unbounded. Oh, sorry, it's 1 over square root of x. 1 over square root of x. Is this what you meant? 1 over square root of x. I want to have a singularity. All I want to say with this example, which is wrong as stated, is that just one bad point can destroy your Frostman exponent. And this does happen. Okay, so we have two problems, and the first problem is about giving upper bounds on slices. So what do upper bounds on slices and Frostman exponents have to do with each other? Well, there is a very simple connection, which is expressed in that lemma, and the proof is here. So we have a measure on R2, or really any metric space, let us say R2, and we have an orthogonal projection onto R, or any Lipschitz map. So all of this is much more general because it's very, very simple. And suppose that upstairs you have a measure, and for the measure upstairs you have a lower bound on the measure of balls. And then you project the measure, and for the projected measure you have an upper bound on the measure of balls. So you have a bound, a lower bound on the Frostman exponent, an upper bound, I guess. But anyway, you have a Frostman exponent for the projected measure. For the measure upstairs, you have an inequality going the other way. In practice, when we apply this, the measure upstairs is going to be extremely simple. So upstairs, we understand everything, and the difficult part is proving this Frostman bound for the measure downstairs. But suppose we know that. Then this immediately gives us an upper bound for the upper box, upper Minkowski dimension, in particular for the Hausdorff dimension of the fibers, for following this very simple argument. So take one point, and this is for every fiber, uniformly for every fiber. Unfortunately, here I use P, here I use pi, here I use X, here I use Y, but it's the same. So let's look at one fiber of this map. And then we have to pick a scale, R, and we have to count how many volts of radius R we need to cover the fiber. That's dimension, right? Yes, but I think it's much easier with the picture. But okay, maybe not for you. Okay. It's something very, very simple. If you don't understand it, I'm very bad at explaining it. So we have a slice of just a projection. So we are just intersecting a line with the setting R2. And we fix a scale R, and we want to count how many volts of radius R we need to cover this slice. Okay, and we can assume that these balls are more or less disjoint, because we take a minimal collection of balls that we need to cover our set, so they have finite overlapping. But all these balls project to an interval of length roughly R, because it's a projection. So these balls are on the one hand, they are morally disjoint, and they all have measure at least R to the T, because this is our assumption. So the measure of the union of the balls is roughly, not roughly, but bounded below by the number of balls times R to the T. On the other hand, when we project, all of these balls fall into an interval of size roughly R. So the projected measure of this interval, so what is the projected measure of an interval? Is a measure of the cylinder. That's the definition of projecting a measure. By assumption, the projected measure of this interval has size at most a constant times R to the S. So we are measuring the one thing in two different ways. By counting how many balls we have upstairs, we have a lower bound and R to the T. On the other hand, looking at this as the projected measure, we get an upper bound R to the S. So we compare both these two expressions, and we get this. So hopefully, even if you didn't understand the actual argument, you understood that it's a very simple argument that I'm too tired to explain. And this reduces the problem of estimating slices to the problem of estimating Frostman exponents for projected measures. Because this argument is so simple, in some sense we haven't really achieved anything, because we have reduced a difficult problem to another problem which is just as difficult, because the reduction is very easy. But for me, this is conceptually very important because I like projections. So I don't like slices, I like projections. Or, I don't know. We know a lot about projections of measures. So this formulation seems more comfortable to me, even though not much has happened. So in particular, we can apply this to the first number slicing problem. There, E will be the product of these two control sets, A and B, and because these two control sets are very nice, they are very simple control sets, we have very natural measures on them, we can take the Cartesian product of these two measures, that will be over mu, and then we can try to apply this lemma. And then what we have to do is estimate the Frostman exponent of this projection. Okay, and this is what I'm saying here. Now, if we take a Cartesian product of two measures, and then we take an orthogonal projection, up to, again, an affable parametrization that doesn't change anything, this means that we are really convolving one of the marginal measures with a scaling of the other measure. Because what is convolution? So convolution of two measures, you can define in many ways, but the convolution of two measures, let's define it in this way, is the image of the Cartesian product under the map xy goes to x plus y. So let's take this as the definition of the convolution. Here, instead of taking xy to x plus y, I want to take xy to x plus lambda y for any lambda. So that means that I have to scale or maybe x plus ty. That means I have to scale one of the measures by t. So, using this very simple lemma, in order to prove this special case, which is just as difficult as the general case of first-number slicing, what we have to prove is that the Frostman exponent of the natural measure on the middle third counter set, combined with the scaling of the natural measure on the middle 1/4 counter set, has the Frostman exponent that you expect. I actually haven't stated what is the conjecture. It was stated in Mungo's talk, but I'm going to state it later. But basically, the problem boils down to showing that this measure, that appears to be very simple because we are convolving two very simple measures, has the Frostman exponent that one expects it to have. Okay, what about the other problem? So in the other problem, there are many, many questions one can ask about Bernoulli convolutions. So in general, the question is how smooth this measure is, and you can measure smoothness in many, many different ways. So for each way in which you measure smoothness, you have a different problem. But Frostman exponent is one way of measuring smoothness. Not the only one by any means, but I think it's a quite reasonable one. So one can ask, what can we say about the Frostman exponent of Bernoulli convolutions? So one can ask, for example, many other questions. This is related to many other questions. So one can ask, what is the Hausdorff dimension of Bernoulli convolutions? So I haven't defined Hausdorff dimension, but morally speaking, in Frostman exponent, we want to control the measure of every ball. In Hausdorff dimension, we want to control the measure of almost every ball. So ball with almost every center, where almost every is with respect to the measure itself. There are results, very, very strong results nowadays for this. And the question is, can we improvement to this? So proving that the Frostman exponent is 1 is stronger than proving that the Hausdorff dimension is 1, because it means you have control of every ball rather than almost every ball. And also, there are methods that allow us to pass from full dimension or full Frostman exponent to absolute continuity. And if the information we know to begin is full Hausdorff dimension, we just get qualitative absolute continuity. But the information we start with is full Frostman exponent. The outcome we get is not just absolute continuity, but absolute continuity with the density that is in every LQ space for all finite Q. So I'm going to come back to this later. Sorry? It's a different nearly all. It's a different nearly all. Yeah. So I'm not saying that for a given lambda, if you know Frostman exponent 1, that lambda also has absolute continuity. We don't know if this is true. I'll come back to this later. We can go from dimension to absolute continuity in this sense by throwing away a zero-dimensional set of lambdas. So I guess this is the answer to your question. Yes? No. Yeah, so my example from before, if you write the actual correct formula, it is in L2, but the Frostman exponent. So basically, no. So the answer is no. L2 density doesn't imply. So Frostman exponent is related to L infinity dimension. It's not related to L2 dimension. It's not related. Well, it is related, but it's smaller, and it can be strictly smaller. Did you have another question? No. Okay. So now we have started bringing these two problems together in the sense that in both cases we want to understand Frostman exponents of certain measures. But in the case of Bernoulli convolutions, the measure is itself self-similar, but with complicated overlaps. In the case of first-number slicing, on the other hand, we have two very simple measures. Simple in the sense that the structure is much simpler because we don't have these overlaps that make our life difficult, but we are taking convolutions. So it's similar but different. So now I want to bring these two similar but different things into one common umbrella. So here is the definition again of Bernoulli convolutions. Is the distribution of the random sum plus minus lambda to the n, everything independent and equidistributed. So there are many ways in which you can alternatively define Bernoulli convolutions. For example, this is a self-similar measure in this sense. So the Bernoulli convolution with parameter lambda is equal to a convex combination, equally weighted convex combination of scaling the measure by lambda and then translating by -1, and scaling the measure by lambda and translating by 1. And this is because you can just condition on the first choice of sign. The first choice of sign is either plus or minus, And once you have the first choice of sign, what follows is the same thing but scaled down by lambda, because the first term is lambda squared and lambda cubed. So just by looking at the definition, you'll see that it satisfies this property. And you can go back, so they are equivalent. Now, instead of writing it this way, let's write it in this way, because it's shorter, and also because it will help us understand what follows. So the right-hand side, or the middle side, so the right-hand side with respect to this, is actually a convolution of the scaled-down copy of mu lambda by lambda, and a measure that is supported on -1 and 1 with weights 1/2 and 1/2. Because convolving, so what does it mean to convolve with an atom at a point A? It just means translating the measure by A. So just by definition, we translate by -1, we translate by 1, and then we give away 1/2. So if you look at this measure, then what we are doing here is just convolving the scaled down copy of mu lambda by lambda with this fixed measure, which doesn't involve lambda. It's just this measure supported on the atoms -1 and 1 with equal weights. And then mu lambda is equal to this convolution, but now we can continue. So this scaled down copy is the convolution of delta with the copy scaled down by lambda square of mu lambda, and so on. So we can keep going. And if we keep going, we get this expression. Mu lambda is the infinite convolution of scaled down copies of delta, where we scale down by lambda to the n. Or if you didn't like this middle part, you can just deduce this from the original definition, just using the fact that the distribution of a sum of independent random variables is a convolution of the distributions. Here we have countably many, but it still works. By the way, what is the definition of convolving countably many measures? Well, for two measures, it's just the push forward of the Cartesian product under x plus y. Here it is the push forward of the countable product under the addition map, which is very well defined here because everything is controlled by geometric progression. So everything converges absolutely no issues with the definition. Okay, so remember this. Mu lambda is infinite convolution, countable convolution of copies where the scaling factor is lambda to the n, and then we are scaling always this measure, which is an atomic measure. In this case, it has two atoms. So this can be generalized by doing exactly the same thing, but this delta, instead of being the specific measure, atomic measure in the previous slide, it can be any atomic measure. And you can do exactly the same, and then you have some natural generalization of Bernoulli convolutions, which is called homogeneous self-similar measures. So in this talk, I'm going to talk about Bernoulli convolutions, but this is sort of a very straightforward generalization. In terms of the construction, basically, instead of taking plus and minus ones, we just take Ti with probability Pi. So instead of taking -1 with probability 1/2 and 1 with probability 1/2, we choose any translations and any weights Pi. And this is the data for this measure delta that appears in this infinite convolution. Any questions so far? So what is important here, and this is why this is called homogeneous, is that the contraction is lambda for all maps. So the Bernoulli convolution is made up of two maps, and they both have contraction ratio lambda. You can do more general things where the contraction ratios can be different. That is not captured by this construction. Yes? In the first definition, yes. Yeah, x to the n should be x to the n times lambda to the n. Thank you. Yes, should be x to the n times lambda to the n. X to the n is what is replacing the random plus minus 1 sign in the case of Bernoulli convolutions. Okay, now let's try to do something similar with the interpretation of first-order slicing in terms of Frostman exponents of convolutions. So now we have these two counter sets, the middle first counter set and the middle 1/4 counter set. And each of these counter sets has a natural measure which has the form from the previous slide. So in the first case, for the middle first counter set, we don't want to have digit 1. That means that we translate by 0 or by 2/3. So maybe let's go back to the picture for a second, although I have to scroll a lot. Right, so 0 is here, 2/3 is here. And then we have two copies placed at 0 and placed at 2/3 with scaling factor 1/3. On the y-axis, we have 0, we have 3/4, and we have two copies placed at 0 and 3/4, scaled down by a factor of 1/4. So this is the reason why we define the corresponding deltas in this way. So delta is everything is uniform because I want to have a measure which is as uniform as possible on these sets. This is why I just use the average, and then I put atoms at 0 and 2/3. And if we do the same thing as we did before with scaling factor 1/3, we get the natural measure, the uniform measure, measure of maximal entropy, measure of maximal dimension, Hausdorff measure. They are all the same measure. They are this measure on the middle third Cantor set. And likewise, we have the natural measure on the middle 1/4 Cantor set. And again, recall that the goal is to obtain bounds, lower bounds. So we want to show that the Frostman exponent of the convolution of this measure with scaled versions of this measure is large. Now, the problem is that even though mu and nu themselves can be written in this form, which is very nice, the convolution cannot be written in this form because 3 is not 4. And not only is not 4, but they are rationally independent. So we cannot do quite this. And now comes, basically there are two main points in this talk. One point is this picture, and now comes the second main point. The second main point is that even though we cannot do this, we can do something that is a slight generalization of this, and that it turns out to be good enough. So let's see it. So basically, okay, so what's the issue? We have powers of 3 and we have powers of 4. And 3 is not 4. But okay, powers of 3 are powers of 3, and powers of 4 are not powers of 3, but they are certainly powers of 3 times something else. And this something else will be driven by an irrational rotation. So 4 to the minus k is 3 to the minus n, where you have to choose n so that 3 to the minus n and 4 to the minus k are almost the same, times something else that depends on k. But the something else is actually an orbit of an irrational rotation. And by the way, this idea was already present in Furstenberg's original paper where he posed the conjecture that was mentioned in Moonstone. Okay, so here is the irrational rotation. I'm going to call it T, and it's convenient to work with the circle at 0 log 4, and I add log 3, but modulo log 4. So I'm really rotating by log 3 over log 4, and this is where it's used that 3 and 4 are rationally independent. Log 3 over log 4 is irrational, so this is an irrational rotation. And then e to the iterating this map n times tan 3 to the minus n happens to be e to the x times 4 to minus another exponent, which is how many times you wrap around the circle when you iterate this. So this is very easy to verify. And just by rewriting things, we arrived at the following. So maybe let's skip this and look at this and then look where it comes from. But look what the conclusion is. So these are the type of measures that I want to understand in order to prove Furstenberg's Lysing conjecture. And I have expressed them in the following way. We have an infinite convolution as before. We have scaling lambda to the n as before. Lambda is 1/3. But instead of having a constant atomic measure delta, we have an atomic measure that is actually a function on our phase space, which is the circle 0 log 4. And this function is either just the atomic measure corresponding to the middle first Cantor measure, or a convolution with the scale copy of the atomic measure corresponding to the middle 1/4 Cantor set. But it's just this. You write down what it means, and you end up with this. So this is what I call dynamic self-similarity. If delta was constant, we would have self-similarity, a very simple form of self-similarity. Here, delta is not constant, it's a function from some phase space, so there is some dynamics in the background. The dynamics in the background here is a rotation on the circle, and delta is a function defined on the circle. And when we do the infinite convolution, we apply delta to the orbit of a point x. And the measure we get at the end depends on x. But you see that all the measures are exactly all the measures that I want to understand. which are convolutions, because by varying x, we vary the scaling. By the way, the scaling could be negative, but everything is symmetric, so it's not important, the fact that e to the x is positive. It's not that the scaling could be negative. The scaling cannot be negative, of course. I guess I also need the flip of mu, but because everything is very symmetric, this is not important. So, okay. Any questions about this? Don't worry too much about following the actual calculation. Just believe me that it's a very simple calculation that shows that we can express a convolution in this form that looks like self-similarity, but we have this dynamics-driven deconstruction. This is why there is the phrase dynamical self-similarity in the title of the talk, and this explains why there is the word slicing in the title of the talk. So now you understand the title of the talk. Okay, so we would like to understand Fresman exponents of measures of this type when either the dynamics is trivial, so you can think that Bernoulli convolutions are also of this form where the dynamics is just the one-point space, so trivial dynamics, or the dynamics is slightly less trivial. So it turns out that what is crucial about the dynamics is that it is uniquely ergodic. So this is very important. But thankfully, irrational rotations are uniquely ergodic. So let's try to generalize this to a more general setting. Okay, I could just work with uniquely ergodic systems, but to be more concrete, because most interesting examples are of this form, I'm just going to focus on translations on compact abelian groups. So we have a compact abelian group, we have a translation on the compact abelian group, and I assume that it is, so it's well known that in this case, it is ergodic if and only if it is uniquely ergodic, if and only if it is transitive. So in other words, if and only if the orbit is dense. So all these things are equivalent, but it is uniquely ergodic. And a particular example is just an irrational rotation on the circle. Then we have our contraction, just some contraction parameter, and then we have our function delta. So what is delta? It's a function that takes us from the group to a measure that has boundedly many atoms. But let's say finitely many atoms, but actually we need a upper bound on the number of atoms. For Bernoulli convolutions, there are two atoms. In the case of the convolution of the middle thirds and middle one-quarter countermeasures, depending on x, the measure has either 2 or 4 atoms, or in some very degenerate cases 3, I guess, but it is upper bounded by 4. Okay, and with this data, I refer to as a model, we can do exactly the same thing as before. We construct these dynamically defined or dynamical self-similar measures generated by the model. By the way, this we can do, okay, so here I haven't told you what is this. But, okay, I did tell you. So this is purely atomic measures on RD. So this we can do in RD. It doesn't have to be R. The examples we've seen so far are in R, but this construction makes sense in exactly the same way in any dimension. Okay, so I call this dynamical self-similarity because it looks like self-similarity, but with some dynamics. But there is another way of seeing this dynamical self-similarity. Suppose that instead of convolving all the way to infinity, we stop at some finite threshold n. Then we get a measure which is atomic. If you convolve finitely many atomic measures, you get by atomic I mean a measure with finite support. Not just one atom, but finitely many atoms. So if you convolve, so the support of the convolution is the arithmetic sum of the supports. So if you convolve measures with finitely many atoms, you get a measure with finitely many atoms. So if you stop the convolution at n, you get a discrete measure, an atomic measure, that approximates the actual measure in some sense, and you get better approximations as n goes to infinity. In fact, these measures converge weakly to the limit measure as n goes to infinity, and because the scaling factor is lambda to the j and we go up to n, you can imagine that at scale lambda to the n, these two measures are the same, but at scales much finer than lambda to the n, these two measures have nothing to do with each other. Okay, and here we can see dynamical self-similarity again. So so we can split this convolution into the first n factors and the rest. The first n factors gives us this discrete approximation, and if we look at the rest, now we are starting the convolution from n plus 1. So we could just take away scaling by lambda to the n, and we get the original thing again, except that we are starting with t to the n of x instead of x. So in other words, we have this relationship that says that the original measure is the convolution of the discrete approximation at scale lambda to the n, and a scale copy scaled by lambda to the n, not of the same measure, that would be self-similarity, but another measure in the family. And the other measure is a measure corresponding to the parameter t to the n of x. So convolving with an atomic measure means taking some affine combination of translates of the measure. Then we scale down, and then we have another measure in the family. So each measure in this family is a convex combination of translations of scaled down copies of other measures in the family. And these other measures are given by these dynamics. So in this sense, this is dynamical self-similarity. Any questions? Okay, as usual, I'm going extremely slowly. Okay, so let's quickly go over some examples. In the case where the dynamics is trivial, we get the homogeneous self-similar measures I mentioned before. Then I explained in an example that if I convolve one homogeneous self-similar measure, such as the middle third countermeasure, and a scale copy of another one, such that the middle 1/4 countermeasure, we get something which is dynamical self-similar, where the group is just the circle, and we can generalize this to convolutions of finitely many measures, and you get tori of higher dimension in this case. Another example that I'm not going to really discuss is if we start with the homogeneous self-similar measure in R2 or Rd, and we project down to R, we also get something which has the same structure. Okay, so the main two examples are the first two ones because they are the ones that correspond to problems 1 and 2 from the beginning. Okay, so what do we want to do? So what is our goal? Our goal is to say something about the Frostman exponent of these measures. Because if I can say something good about the Frostman exponents of these measures, I have solved some version of problems 1 and 2. So this is what we want to do. And it turns out that there is such a result, but it has an assumption. Some assumption is necessary. We don't know. Okay, this is very likely not the sharp assumption, but this is what we can do. So we have the concept of exponential separation. This idea of exponential separation comes from Mike Kochman's fundamental work on self-similar measures, and this is an extension to the dynamical setting. Recall that if we stop the convolution at the finite level, we have an atomic measure. So it has some number of atoms, some finite number of atoms. So we can look at the smallest distance between these atoms. So when does exponential separation hold? Exponential separation hold when for almost every x, so recall that we have a group. Our phase space for the dynamics is a group, so it has a Haar measure. So we can speak of almost every. It's almost every with respect to the Haar measure. So suppose that for almost every initial point, so for every point we have a different sequence of approximating measures. So I want something to happen for almost every point. What I want to happen for almost every point is that the atoms of these discrete approximations are not super exponentially close to each other. In other words, I want an exponential lower bound on the smallest distance between atoms of the discrete approximation. And this R can depend on X, so everything is as general as you could possibly want. It's very, very, I wouldn't say, okay, it is very weak, but also we don't need it for every n, we need it for infinitely many n. So this is in some sense very, very weak. So as I mentioned, in the self-similar case, this is exactly the notion of exponential separation introduced by Mike Kochman. And in the self-similar case, where the dynamics is trivial, this condition is very hard to verify. It's very mild on the one hand. It almost always is satisfied, but if I give you an example, it's very hard to verify for that example. But on the other hand, something magical happens, which is that when you have non-trivial dynamics, this becomes much easier to verify. So you could imagine that if you have dynamics, things, instead of trivial dynamics, if you have real dynamics, things will be more difficult. But actually, things are much better. When you have dynamics, this becomes, in some cases, trivial, or certainly much easier to verify. And the reason is that we only need to check it for almost all elements in the group. Not for all. It wouldn't be true for all, in fact, for almost all elements of the group. And if the group has one element, almost all is all. And this is why it's more difficult. Okay, any questions about this property? Okay, now we can state a theorem, which says that if we have a model as before, and we have some very, very mild technical assumptions that you can ignore, very, very mild, and exponential separation, this is an actual assumption, then the Frostman exponent of every measure generated by this model is what you expect. And this is what you expect. Don't ask me why this is what you expect, but it is what you expect. In the sense that this is always an upper bound. Without any assumptions, this is always an upper bound, which is easy to prove. So this is the most natural conjecture to be also a lower bound. And the theorem says that under these assumptions, model with exponential separation and very mild technical assumptions, this is indeed the truth. Is defined here, is the largest. So this is a measure with finitely many atoms. We look at the atom with the largest measure. That is the infinity norm. So for example, for Bernoulli convolutions is 1/2. And for the convolution of mu and nu, it's either 1/2 or 1/4, depending on x. You have to integrate, but the point is, it is what you expect. It doesn't matter what it is what you expect. And in fact, it is what you expect because it is the reality. So this is actually the Frostman exponent. So there is something that is very hard to understand here, but the paper is 10 years old. So far, nobody has found a mistake. And I know that many people have read it carefully. So it's still, I hope it's true, but it's still sort of magic, which is that exponential separation is something you need to check for almost every x, but the conclusion is true for every x. And this is fundamental, that we can get a conclusion for every x. Okay, in some sense it's not so surprising because there is unique ergodicity behind it. So the reason why we can go from almost everywhere to everywhere is because I'm assuming that the dynamics is uniquely ergodic, and in some sense this is why I'm assuming that the dynamics is uniquely ergodic. Any questions about this theorem? Okay, so now we have solved problems 1 and 2. Right? We have the answer to what is the Frostman exponent of the measures for which we wanted to know what is the Frostman exponent. Here is the Frostman exponent. Okay, so for Bernoulli convolutions, we have not really solved it because we have this exponential separation assumption that we don't really understand. And also, again, there are many questions one can ask. So we have not really solved it, but at least we have proved something new. Okay, so if you know what is the LQ dimension of a measure, so there is Hausdorff dimension. Hausdorff dimension is morally L1 dimension, and there is Frostman exponent. Frostman exponent is L infinity dimension, and there is a family of dimensions that interpolate between these two called LQ dimensions. If you know what those are, the theorem also works for LQ dimension. So the LQ dimension is what you expect. In fact, that's how it's proved. So the theorem is proved for finite Q, and then the case infinity is just obtained as a limit. Okay, as I said, it's not really important that you have an abelian group. So the algebraic structure, so it doesn't have to be any algebraic dynamics in any way, but it does have to be uniquely ergodic. Okay, so when we go to Bernoulli convolutions, there is no dynamics. So exponential separation just means exponential separation of cutting down this random sum at a finite stage. So if we cut it down at level n, we have 2 to the n atoms. And exponential separation means that these atoms are exponentially separated for infinitely many n. And again, in the case of Bernoulli convolutions, this notion was introduced by Mike Hochman, and Mike proved 2 easy lemmas, easy but important lemmas. One is that exponential separation is very, very prevalent. So the family of parameters lambda, for which we do not have exponential separation, has 0 Hausdorff dimension, even 0 packing dimension. So exponential separation fails on a very sparse set of parameters. Unfortunately, we don't know which parameters, but at least we know that it's very small. And if on one concrete parameters lambda for which we know that exponential separation holds, well, the exponential separation holds for any algebraic parameter lambda for which there are no exact overlaps and no exact overlaps. So exact overlaps means that some of these combinations are actually 0. So this is exact overlap. So exponential separation means these things are not close to 0 in an exponential sense. No exact overlaps means just non-zero. And this is the gap that we still don't understand. Okay, so a corollary of the main theorem, immediate corollary, is that if the parameter lambda has exponential separation, then the Frostman exponent of the Bernoulli convolution is 1. Mike Hoffman proved this with Hausdorff dimension, and as I explained before, this is a much stronger statement, because it means every ball has radius at most r to the 1 minus epsilon for any epsilon, when r goes to 0, in a uniform way, uniform over all the centers. Okay, and then I come back to what I mentioned before, that once we have full Frostman exponent, we can say something about density, a corollary of the corollary, using an idea that I introduced and then refined together with Boris Solomiak. So a double corollary is that nu lambda is absolutely continuous with an LQ density for every finite q, outside of a set of exceptions of 0 Hausdorff dimension. So we actually lose a set of 0 Hausdorff dimension twice. In assuming exponential separation, we are throwing away a set of dimension 0. And then to go from full Frostman exponent to LQ density, we throw away another set of 0 Hausdorff dimension. But thankfully, the union of two sets of 0 Hausdorff dimension still has 0 Hausdorff dimension, which is why we have this corollary. Okay, so if instead of Frostman exponent we look at Hausdorff dimension, there is an absolutely major, striking, and unbelievable theorem of Peter Variu following lots of previous work of Breillat and Variu that shows that actually nu lambda has full Hausdorff dimension whenever lambda is not algebraic. So algebraic lambdas are still very mysterious, but for every transcendental lambda, then the Hausdorff dimension is 1. In particular, there are only countably many, because algebraic numbers are countable, there are only countably many exceptions to full Hausdorff dimension of Bernoulli convolutions. Recently, Mungbu, well, not recently, but the preprint came recently, Mungbu proved that the set of exceptions is countable in a much simpler way. So this proof is very complicated. So the actual paper is 8 pages, but it builds on some very heavy stuff. Mungbu has a much easier proof of the fact that for Hausdorff dimension, the set of exceptions is countable. Okay, so I think an interesting question is try to extend this theorem of Variu to Frostman exponents. Following Variu's original proof, this seems very, very hard, but now we have this approach of Mungbu, so maybe one can combine both and try to do something to address this open problem. Any questions? So do I have something like 7 minutes? Okay, great. I was not going as fast, as slow as I thought, or maybe now I'm going too fast, most likely. Okay, so what about the second problem? Okay, so before I stated just a special case of Furstenberg's intersection conjecture. This is the actual conjecture, which most of you probably saw in Moon's talk, but let's state it again. The conjecture says that the middle third Cantor set and the middle 1/4 Cantor set can be replaced more generally by closed invariant sets under multiplication by P and by Q on the circle, assuming that P and Q are not secretly the same number. And not being secretly the same number means that P and Q are not integer powers, natural powers of the same integer, or in other words, the ratio of the logarithms is irrational. So if we have two Cantor sets coming from different bases, then their intersection should not be too large, and this should still be true when we apply an affine map. So we perturb one of the sets by an affine map, and okay, this is the actual bound. And this follows immediately from the main theorem. So you have to prove exponential separation for the model, but because the dynamics is now a circle, so the group is a circle, it's not trivial, it is very easy to check. And then you have to compute that the S appearing in the main theorem gives you the right value in order to apply this lemma, but that's a very, very simple computation. So it does work. So it's really an immediate corollary. Okay, just a historical remark that was not in Moon's talk. So Moon gave many historical remarks, but maybe let me mention that. So sort of the philosophy behind this conjecture and many other conjectures of Furstenberg is that expansions to base 2 and to base 3 have nothing to do with each other, And a bit more precisely, invariant sets under times 2 and invariant sets under times 3 have nothing to do with each other. So Furstenberg proved this if nothing to do with each other means not being the same set, which is a very weak notion of having nothing to do with each other. Okay, of course, with some trivial exceptions. The whole circle is invariant under anything you want, but it's not a very interesting set. Okay, this shows that A and B have nothing to do with each other in a much stronger sense. Their intersection is very small. Not only they are not the same set, but if you intersect them, the size goes down by a lot. By the way, this is sharp. You cannot put anything better on the right-hand side if you want this to be true. Okay, so some remarks that were already in Moon's talk. Well, one that this was also proved by Moon. I will run out of time by telling an anecdote. When I was working on this problem, I had a strategy. I hadn't written down the details, but I was confident that it worked. But I didn't mention it to many people. And around this time, which was 2015, I think, I visited Oulu to work with Ville Suomala. Mongbu was a postdoc at Oulu at that time. Okay, and Ville told me, I didn't tell anything to Ville, but Ville told me, Moon thinks he has a proof of Furstenberg's intersection conjecture. So I had to say, me too, at that point. And then we talked, and we saw that our proofs were completely different. So we decided to, well, not merge the papers because the proofs were just totally different, but we agreed to synchronize our submission. So you will see that the two papers on the archive appear on the same day. Okay. Okay, and as mentioned in Moon's talk, Han Yu simplified, in some sense, and also made more quantitative Moon's idea when the sum of the dimensions is small, and then Tim Austin found an even shorter proof. These three proofs are dynamical in nature, and in some sense, all three are based, as Moon said, on an idea that Furstenberg already had in his original paper. But of course, there has to be new ideas. If Furstenberg couldn't do it, by definition, it means that you need some very, very clever new ideas. So the ideas in these two papers, they're, okay, both rely on Furstenberg's original approach, but have an extra idea, and in both cases, it's extremely clever. Okay, instead of slicing, so you can slice many things. So instead of slicing the product of a times 2 and a times 3 invariant set, you can slice, for example, the Sierpinski carpet. And if you slice the Sierpinski carpet, well, you have to be careful because the Sierpinski carpet contains lots of segments. So it's not true that the intersection with any line will have small dimension, of course. But if the line has irrational slope, then it is true. We get the same bound. So the dimension of the Sierpinski carpet with the line with irrational slope is at most the dimension of the carpet minus 1. And the same is also true for any real analytic curve which is not a line with rational slope. And even more general, but this is just an example. Okay, so after the paper came out, there was a lot more work, and I mentioned in just a very small subset of them. So these are some works that use the main theorem on Frossman exponents. There is work of Osama Khalil on the functional approximation of fractals. Then people used the Frossman exponent result to study Hausdorff dimension of self-affine sets in the plane, also to study what happens when you push down an ergodic measure on a self-similar set. For example, for Bernoulli convolutions, the underlying measure symbolically is the 1/2 Bernoulli measure. But instead of having that measure, you can push down. So you have the map given, so you have a symbolic space which is plus minus, sequences of plus minuses. On this symbolic space, you can put an ergodic measure, and using the Frossman exponent result for self-similar measures, Jordan and Rappaport obtained the dimension of ergodic measures, which was not known until then. And then you can do things on the integers. Maybe I should also mention Joel's work with his authors. Apologies, but you can deduce things. In fact, well, what they did, I think, is more interesting than this. In fact, so double sorry. But anyway, you can deduce about things about looking at sets with restricted expansions in the integers. So now I have 30 seconds. So as Monk said, in my proof I use a lot of additive combinatorics. And I was hoping to give a very quick flavor of that, but I don't have time. Maybe let me say that the additive combinatoric parts of the proof also found applications in other problems, and including some work in progress. And just to finish very quickly, one can ask about higher rank versions of this problem. And again, as mentioned in Moon's talk, together with my former postdoc, Emilio Corso, we have extended the main result from Frostman exponents to higher dimensions. This is not so simple because there are well-known issues with higher dimensions, and also because the proof in one dimension just doesn't work at one critical step. So we have to find a way to go around this issue, and this way to go around actually simplified the proof even in one dimension. And in particular, we proved a higher rank version of Furstenberg slicing, where instead of taking the Cartesian product of two sets, we take the Cartesian product of d sets. One invariant of the multiplication by 2, another by 3, another by 6. So it's quite surprising that 2, 3, and 6 works. You might think that it shouldn't, but it does. 12, 24, and 57. No, 57, why not? Okay, and then you slice it with a plane, but now you're in RD, so you have many choices of dimensions of planes. Take your pick. Any dimension works, and then we have the natural formula and the natural assumption. There are some assumptions, but these are the sharp assumptions. So these are the weakest possible assumptions. Okay, now I'm done. Thank you very much.
Thank you very much for the beautiful talk. Questions and comments?
I have two questions. First one, do you have some results beyond the P? For example, is it possible that it has smooth density sometimes?
Sorry?
Possible that density is smooth for some?
Density is smooth. I mean, maybe. We have no idea. It certainly doesn't follow from. So the only thing that is known is something that, for Bernoulli convolutions, the only thing that is known is something that Erdős proved in 1939, which is that if lambda is very close to 1, then for almost every lambda you have a CK density. This is true for every k. The larger the k, the closer to 1 you need to go. And we don't know anything else. We don't know any other way to prove that. So we don't know.
Secondly, if you take measures which are not atomic, in your definition, what happens?
Well, this will make things easier. So everything will be smoother. So I don't think it's too important that they're atomic. In some sense, this is the interesting case.
Questions? Okay, let's thank the speaker and all other speakers this afternoon.